This lesson, we will be talking about homologous series and functional groups as it relates to topic 10, organic chemistry. Now, my first question that I have for you is, why do we need functional groups and what is a homologous series? Now, the thing with carbon and carbon chemistry, which we call organic chemistry, is that there's so many compounds. There's more organic compounds than all the other compounds put together. So therefore, we had to find a way to systematically identify these compounds and name them. And this is where the functional group and subsequently the homologous series comes in. Let's go. So, our first question, what is organic chemistry? I gave it away on the first slide, but maybe first of all, it's the chemistry. It's not the study of the chemistry of life. So a lot of you might think, well, it's everything that's living. That's organic chemistry. No, it's not everything that is living. A lot of things in organic chemistry are pretty dead for a little while. Oil, fossils, wood, that's petrified, and a lot of other things. So it's the study of carbon compounds, specifically carbon compounds containing a carbon-hydrogen bond. So the chemistry of carbon is more extensive than that of any other element. There are more carbon compounds than all the other elements put together. And that's what I said at the start. This is why it's a separate branch of chemistry. And sometimes people will say it's a whole different set of chemistry. And furthermore, why is carbon so special? Why does it have this ability to form these large amounts of compounds? This is related to a property we call catenation, which enables carbon to form chains and rings. So our first family of organic compounds, or our first class of organic compounds that we meet, is alkanes. Now, alkanes are often called saturated hydrocarbons. Now, what does saturated mean, and what is a hydrocarbon? If you look at the molecules here on the right of the screen, you will see that all of the carbon-carbon bonds are single bonds. That's why we say it's saturated. If there's only single bonds between carbons, then we say it's a saturated hydrocarbon if it contains only hydrogen and carbon atoms. So in organic chemistry, we say that a class or family of compounds is a homologous series. Now, what is a homologous series? A homologous series is a family of organic compounds that all look similar. They only differ in chain length. But when we add something, we add something that is similar in the rest of the chain. So in the case of the alkanes, we just add another carbon, which makes more bonds with hydrogens. So it is specifically defined as a series of compounds that have the same functional group. Each member differs from the next by a common structural unit, usually CH2. Now, in the case of alkanes, there is no real functional group. We will see just now what a functional group is, but they don't really have a functional group because we only have single bonds between carbons and all of the carbons are bonded to hydrogen atoms. That's the functional group. It's just a carbon that can make 4 bonds and it will only bond to carbons and hydrogens. But it doesn't specifically have a functional group like the other families that we will meet just now. It also has a general formula, CnH2n plus 2. Now, what does this general formula mean? It means that if, for example, I have a carbon with a hydrocarbon with 2 carbons, then it must have the formula H 2 times N is 2 plus 2. So in other words, the formula of this alkane should be C2H6. And if you look over here, you will see that C2H6 is called ethane. And so we can replace the N with any number of carbons and we can get the whole formula for that specific alkane. So our first checkpoint, this is what you have to do. Determine the molecular formula for the alkane with 30 carbon atoms. I'm giving you a few seconds, so quickly take out a piece of paper and see if you can find the molecular formula. Okay, you're done. So 30 carbon atoms means that in the general formula CnH2n plus 2, I will replace N with 30. So in other words, it then becomes C30, H2 times 30 is 60 plus 2, 62. So C30H62 will be the molecular formula of the alkane with 30 carbon atoms. One with 48 hydrogen atoms. Okay, now we need to reverse engineer it. You think you can do it? Okay, so if we reverse engineer it, we first need to subtract the 2 that we would have added to it. So that gives 46, meaning that 2n must be 46. Now, if this confuses you, just equal 48 to 2n plus 2. So then 2n must be 48 minus 2. So that's 46. So n then in this case must be 23. So in other words, our formula will be C23H48. Okay, I hope you got them right. So if we talk about the alkanes further, we can say the following, that each one of them just differs by an addition of a CH2 group. If you go and look at the difference between methane and ethane, you will see that we've just added another carbon with 2 hydrogens. So in other words, what I'm saying is that going from methane to ethane, I added another CH2 group. Going from ethane to propane, I add another CH2 group, and so on. Now, I want you to notice something, guys, how we count in organic chemistry. Meth, 1, eth, 2, prop, 3, but, 4, pent, 5, hex, 6. Now, in IB chemistry, you only need to know how to count up to 6. So, pretty easy. A homologous series we can identify by functional groups. Now, like I said earlier, for the alkanes, we don't really have a functional group because a functional group is the atom or group of atoms in a molecule that gives its characteristic chemical properties. So in other words, how it reacts with other compounds. In the case of our alkanes, we only have single bonds between carbons and hydrogens, and it's not really a definite functional group, but it changes quickly from here onwards. Before we go on, we need to talk about the different types of formulae that we get. So the first type of formulae that I want to talk about is an empirical formula. Now, in an empirical formula, it's the simplest whole number ratio of the elements present in a compound. So the example they give us is C2H5. Now you must wonder, what is C2H5? Well, nothing in particular, but we do get that butane can be C4H10. And the simplest ratio of these atoms to one another can be C2H5. So C2H5 doesn't represent a specific compound, but it is the empirical formula of butane, the simplest ratio in which we can find the atoms of butane bonded to one another, if that was possible. Then the molecular formula indicates the correct number of atoms for a certain compound. So in other words, in the case of butane, we need 4 carbon atoms and we need 10 hydrogen atoms. So we will just indicate C4H10. However, a molecular formula doesn't tell me anything about the structure of a compound. That's why we have structural formulae. And structural formulae shows all the atoms and bonds in a molecule. So in other words, I will indicate every single bond between a carbon atom and a hydrogen atom. I can also get a condensed structural formula. So in a condensed structural formula, I still want to see the structure of the molecule, but I don't want to indicate every single bond. So I can simplify it. I can say, well, on the first carbon, I've got 3 hydrogens bonded, so it's CH3. Then on the second one, I've got 2 hydrogens bonded, so it's CH2, and then it's again CH2, and then it's CH3. You could have written it H3C, CH2, CH2, CH3. There's no difference. There's no preference as well. CH3, CH2, CH2, CH3. It's all of the same. Because if you were to get to the structural formula, you would need to draw it out, and hydrogen will not make more than one bond because it has a valency of 1. It's in group 1. And we know carbon, in the case of organic chemistry, always makes 4 bonds. So that's our check when we go from a condensed structural formula to a full structural formula. The last type of formula we get is what we call a skeletal formula. Now, a skeletal formula might just look like a zigzag line, and it might not seem very significant, although it is a type of formula which is used very often in the international chemistry communication. So in a skeletal formula, a line represents a single carbon. So the start of the line there would represent the first carbon. Where it makes an angle, it indicates that there must be a second carbon. Another angle indicates it's a third carbon, and then the end of that line indicates there's the fourth. So I'm only indicating where my carbons will be, and the hydrogens I'm not indicating at all. But because we all know that the international community uses these skeletal formulas, we can interpret meaning into those zigzag lines. So as we develop this course, you will see how we do it for other functional groups as well. So here we have a representation of our first 6 alkanes and all of the different formulae we could represent them with. I leave it up to you to go through this and study it on your own time. We can also represent molecules in other ways. So we get computer generated images, and you will spend some time doing some modeling work on a 3D site where you will model different molecules. So one could be the stick model, where we represent, once again here, it will be the angles that's changing that indicates that there must be a carbon, and there must be a carbon, and there must be a carbon, and there must be a carbon. And on those carbons, the white parts indicate there must be hydrogen atoms bonded to those. Okay, so and here there must be, in the case for carbon, to have 4 bonds. You will see 1, 2, 3, 4 bonds there. So that is a stick model. We could also have a ball and stick model. So the sticks indicate the bonds. So that's a bond, and that's a bond, and that's a bond, and that's another bond, whilst the balls then indicate atoms. The white balls here indicating hydrogen, and the grayish ones indicating carbon. Or we could have a space-filling model, which here looks like a caterpillar, whilst the big balls represent carbon atoms, and the smaller plugs on them, like the feet of the caterpillar, represents the hydrogen atoms. Okay, now each of these models have their reason for existing. Some of them are more useful than others. For example, the space-filling model doesn't really give you that good idea of the structure, because some of the atoms aren't really visible. If you, for example, take the hydrogen atom that must be present on that carbon over there, you don't see the other hydrogen. So it's not ideal to use a space-filling model, but it might be just for graphical reasons that you might want to use it.